divided by length. The minimum size is 4 lambda divided by 2 lambda. Sometimes it's also called 1 unit. For example, there's a 600 nanometer process which has a width of 1.2 micrometer and the length of 0.6 micrometer. If you look at the inverter circuit here, there is a PMOS at the top which has a width of 8, while the MOS is 4. Is there anyone who knows why the PMOS should have wider width than MOS?
Because its mobility is half slower.
Yeah, that's true. So to balance out the current in between the PMOS and MOS, we need to make the size different. So for the whole process scheme, since the transistors are built horizontally, it's called planar process. And we built it over the silicon, the wires are built over the silicon dioxide through the via or pores that I mentioned before. And then connect the material on 2 layers, like you can see here. And then they should be manufactured in very clean rooms, clean areas, because we are dealing with micrometer or sometimes to the sub-nanometer regime. For our Marcos building, Marcos clean room, we have a class 100, which means we have approximately 3,520 particles within cubic meter. For typical urban areas like here, it would be like 35 million particles per cubic meter. For industry, it should be a lot cleaner. So this is a random photo taken in the Marcos clean room entrance. I don't know who they are. So we can summarize these 4 steps into 5, like in the right side diagram. So we started with wafer preparation, and then we used diffusion and polysilicon gate, and then we connected the metal, and then passivated the device. So the top 3 process flows are included in the front end of the line, and the last 2 will be a back end of the line. And this is basically a repetition of these 3 processes, like patterning, and then deposition of the material, and then we process the material. After fabrication of the devices, we need to test it. If it is functional and parametrically what we wanted can be achieved. So we didn't go through this passivation process yet. So there is a packaging process. So after the wafer is fabricated, we saw or cut it into pieces to make chips. These chips are packaged using the connections of using the pins, and we passivate it to protect it from the environment, surrounding environment. So these are brief explanation on packaging. And we also didn't go through how this photolithography actually works. So you can see here in the right figure, there is a lens here, and then the light source will be on the left side of it. And then if we emit the light through the lens, and then there is a sample in the right side, and there is a certain distance of D, capital D here, and then a certain angle, which is theta. So using these values, we can find what resolution we are going to have. Using this Rayleigh's criterion, which explains that the diffracted patterns here, the top peak, the first peak, and the first minimum are matched in the first place. We can there at that point we compute the resolution, which is equivalent to some constant times lambda, which is a wavelength here, divided by numerical aperture. This numerical aperture is the ability of lens to collect diffracted light. It can be computed by multiplying the reflective index of the lens times sine theta. Then we can get the resolution. This resolution is proportional to this wavelength, so it is largely determined by the wavelengths of the light we are using. For extreme UV light case, it has approximately 124 to 10 nanometers. For example, there is a KRF laser, which has a wavelength of 248 nanometers. And yeah, by plugging this number into the wavelengths here for the resolution, we get 310 nanometer. There is no explanation on this constant and numerical aperture, but this is just an example case. These are mostly UV light. For the visible light, we are able to see. They cannot be used for the CMOS process because it has too large wavelengths for modern feature size. There are a couple of techniques that we can improve the resolutions further. So lastly, the CMOS industry do not want to fail many transistors when they are making the chips, because they have to get the maximum profit from their work. So we have a figure of merit in this case, which is called yield, which means fraction of chips that properly works in the chip. It can be computed by exponential to the area of times defect density. So if area becomes large or defect density gets large, this yield, which is a fraction of the chips that actually works, decreases. This yield depends on each step, so it will be some of the failure that we had in the previous steps up to the point we finish. These manufacturing problems arises because of the natural variations that is difficult to control. These manufacturing problems can affect parameters like device current, which will result in slower speed and so on. For the device industry, we have two divisions. So for the first, we have process engineers, and the other we have the circuit designers. So for the process engineers, they mostly take care of this single device, like transfer curve or output curve or transconductance and single device oxide thickness and wire thickness. On the other hand, circuit designers look at the transistor size and wire width and length. This is a history of around 20-30 years before, and you can see the trend that it's decreasing by 0.7 in each 2 or 3 years, which follows the Moore's law. So this is the brief history. Yeah, thank you very much for listening to my talk. And the rest of time will be taken care of by Dr. Wang Boshim here with the VNet. Thank you.
Okay. Second topic is about 3D and fabrication. My name is Wonbo Shim, and I'm also a postdoctoral researcher at the Professor Shimang's group. And during my PhD course, my major was 3D and fabrication, and also I was working in Samsung Electronics, and I was in NAND flash design team. So today I will gonna explain about the 3D NAND fabrication process. This is my email address. So